Here we're going to look at buffers and how buffers work, the qualitative way buffers work. You've been given a definition of a buffer there. It's that buffers resist the change in pH upon additions of small amount of acid or alkali. Now, there are two types of buffer. There is an acidic buffer and a basic buffer. We're going to concentrate mainly on acidic buffers because it's only really acidic buffers which will be asked in terms of quantitative, that is amounts and calculations. If you do get a question on basic buffers, they're likely to be just understanding them in terms of Le Chatelier's principle. No calculations will be necessary. So let's firstly then have a look at acidic buffers. We'll look at that in a bit of depth, and then we'll just very briefly take a look at basic buffers. So acidic buffers. An acidic buffer must contain significant quantities of weak acid, HA, and the salt of the weak acid, A-. So for a buffer to work effectively, it must have significant amounts of each of these two species, the HA and your A-. There are two ways in which you can make an acidic buffer. You can add solid A- to the weak acid. So you can add a known mass of your salt to your weak acid, and there you get a buffer solution. Because remember, the buffer would need significant amounts of this and this. The weak acid on its own will have plenty of HA, but will have hardly any A-. So we just add in more A-, so we get significant quantities of both these species. The other way in which we can make an acidic buffer is by adding hydroxide ions, a solution of hydroxide ions. And what happens there is by adding hydroxide ions, we'll actually make the A-, will form A- according to the following equation. In order for this to be a buffer, you must add hydroxide ions to an excess of your weak acid. So the weak acid has to be in excess in order for this to be a buffer. So you add hydroxide ions to a weak acid, and by doing so you will produce significant quantities of your A-, and that will therefore give you a buffer solution. So they're the two ways in which you can make a buffer, an acidic buffer. You add the a fixed amount of solid A- to a weak acid in order to produce significant quantities of both of these, or you can add hydroxide ions to an excess of weak acid, and again, by doing so, you'll get significant quantities of each of these. So what we're going to look at then is how does an acidic buffer resist changes in pH. And the first thing we're going to do is by what would happen, or how does a buffer resist pH when small amounts of acid are added, strong acid are added. So what we're going to do then is, how is it going to resist a change in pH? By adding X moles of hydrogen ions, which is my strong acid like HCl or H2SO4. What we're going to have a look at then is we'll have a look at the dissociation of a weak acid, and I will actually just use HA for my weak acid. And that dissociates, as you know, into H plus and A-. So let's have a look. Using Le Chatelier's principle, how would adding hydrogen ions affect the equilibrium? So remember, we'd always start by saying if you add hydrogen ions to this equilibrium, the equilibrium would shift to oppose change. We would say then the equilibriums would shift to decrease the hydrogen ion concentration, and therefore the equilibrium would shift to the left. So what we're saying then, in this particular instance, the equilibrium is going to shift in this direction. It's going to shift to the left. And in doing so, you are going to produce more HA, and you'll decrease the amount of A minus. So in the process, what you will do then is the HA moles will increase by the number of moles of H plus that are added, and your moles of A minus will decrease by the number of moles of H plus added. Okay, so that's what occurs when X moles of hydrogen ions are added to a buffer solution. You've got the qualitative explanation, and then we've got a bit of an insight into quantitatively what will happen. The equilibrium will shift to the left to oppose the change, and the number of moles of HA will increase by that amount, and the number of moles of A minus will decrease by this amount. Let's have a look at what would happen in the addition of X moles of hydroxide ions, which is again a strong alkali. So again, let's have a look at my dissociation of my weak acid. And again, let's have a look in terms of Le Chatelier's principle. If I add hydroxide ions, again, what's going to happen? The equilibrium will shift to oppose the change. Now, adding hydroxide ions, the hydroxide ions will react with these hydrogen ions. So the equilibrium is going to shift to oppose that, and it's going to shift to increase the concentration of hydrogen ions. So the equilibrium will shift to increase the concentration of hydrogen ions, because the hydroxide ions are going to react with these hydrogen ions, and therefore we would say the equilibrium shifts to the right. So what we're going to say in this particular instance, the equilibrium is going to shift in that direction. And in doing so, if we're shifting it to the right, then the number of moles of A minus will then increase by X. The number of moles of A minus will increase by this amount, and the number of moles of HA will decrease by this amount. So again, we've got the qualitative explanations here, and then we can see got a bit of a heads quantitatively how that's going to change the proportions of these buffers. Now, when we're working out the pH of a buffer, this is how you do it. The Ka is equal to H plus times A minus over HA. And what we've got to do is we've got to rearrange this equation in order to produce this. Now, this is not a weak acid. We can't assume H plus is equal to A minus anymore. So we've now simply got to rearrange this equation to give you H plus. And when we rearrange that equation, we get Ka times HA over A minus. And that there is the equation that you would need to use if you're asked to work out the pH of a buffer. I'm going to very, very quickly discuss basic buffers. So if you've got a basic buffer, this would be something like NH3, which is a weak base, and a salt of the weak base. And we can set up the following equilibrium. That'll give us NH4 plus. And we can apply the same rules to the same principles as what we did when we looked at acidic buffers. So if we add hydrogen ions, I'm hoping you can see what was going to happen to the equilibrium. Equilibrium shifts to the right to decrease your hydrogen ion concentration. If we add hydroxide ions, hopefully what you can see is very similar explanations as we did for the acidic buffers. The equilibrium shift to the left to increase the hydrogen ion concentration. And by doing so, by doing these things, it will maintain the pH. It'll keep the pH relatively constant. So that's how buffers work in a sort of a qualitative way. I've not looked at any particular numbers there and calculations, but certainly when we come to look at this bit here, we're going to use these principles here in the next few videos to show how we can use this bit here to work out the pHs of buffers, or how the pH of a buffer changes upon small additions of acid or alkali.